Hi there, it's Martin Pusic. You already glimpsed my last slide, so the punchline's gone. But at any rate, what I'd like to talk about today is kind of let me just figure out how I change slides. There we go. Is kind of an evidence-based practice user's guide, or at least that approach, to certain selected topics in education research, and specifically education research, the way it applies to simulation. And so most of you know that the user's guides were developed and published by JAMA a number of years ago, and look to make accessible the idea of assessing study design and making sure that the studies that we consume for our clinical practices are up to standards, and so that we can tell what's a good study and what's a poor study. And in my journey, you know, sort of as a clinician, I learned this stuff and thought it was great, and thought it was a wonderful way to make transparent all the mysteries of the way clinical research worked. But then when I changed mid-career to focus more on education and to get further training on educational science and educational studies, I kept on trying to apply clinical research principles, and found that in many respects and in many aspects they did not apply to educational studies, and so that and it took me a long time to set aside some of the clinical biases that I had in favor of a more adaptive educational ones for what I was trying to do. And so as I went along, I sort of painfully learned some of this stuff. And so my motivation for today's talk is to show you a few of the things that weren't readily apparent to me starting off, but that are important in terms of the validity of an educational study. So the evidence-based practice folks have a framework in which they ask three main questions of any study, and then the actual way you answer these questions is different depending on the study context. And so our main questions are: is it valid? What are the results, and can we apply those results? And this goes from sort of internal validity to result representation to external validity, but couches it in more accessible words. And what we're going to do today is approach this: is it valid for educational studies? And I'm choosing, there's a lot of things that we could look at in terms of validity for educational studies, and I'm purposely going to ignore the ones that we already, as clinicians, have a sense of, and instead focus on these three that are specific to educational studies: contamination, the issue of pre-testing, and then measures of reliability. And then next month we're going to look at what are the results, and specifically talk about effect sizes and why that's a better way of representing the results of an education study, and then talk about the mysteries of calculating a confidence interval around effect sizes. So I hope to see some of you there. Okay, so the framework we've got, and now we're going to look at is it valid? And the first thing we're going to talk about is, in an educational study, you often have an imperative to look at groups and talk about whether they're comparable at the start. So that we're sure when we randomize people to two groups, did we randomize two groups that were comparable? And here's a typical study design. You approach some learners who meet the inclusion criteria that are important to you. Typically you would pre-test them and then randomize them to either getting an intervention. Let me just get a pointer going here. So to an intervention group or to a control group, and at the end post-test everybody, and then try to determine whether or not the intervention group did better than the post-test group did. And so our question right now is to focus first on this pre-test and talk about whether or not that's a helpful thing, and then secondly on this issue of contamination. So what we're hoping for when we do our study is to pointer out of your way, is to see whether our control group did better. So did better on this post-test than our intervention group. And here, you know, sort of it was a computer trial, so that whether or not the computer group did better than the control group. And here we can see that in this particular study, in terms of their score out of 10 on this exam, there's something of a difference on the post-test in the computer group. And so is that meaningful? And especially, you know, sort of would it be more meaningful if the one group scored higher on the pretest than the other group? And what we're hoping is by pretesting, then we can come up with an integration that then gives us a sense of the difference being greater in one group than the other, and will this be more meaningful than it would be otherwise. And so when I first started doing this, it seemed to me obvious that you wanted the pretest, and so that so more information the better. And by having a pretest, I had a sense of where people were at, and therefore I could I would have more of a sense of how much people had learned across my study, and will have gained insight into knowledge gain scores, and that was the way to move things along. But consider the negatives of pretesting. In essence, a pretest is an intervention. And so that when you give a pretest, it basically primes your learners, and so that it makes them pay attention to certain things that then when the intervention comes along, or even when the control comes along, they are different from what they would have been like if there had been no pretest there. And the problem with this is that the pretest may interact with the intervention in a way that you have no access to. You have no idea how the pretest primed the person and how it set them up. And so that so it may advantage one of the two groups that you're trying to contrast. And in fact, the whole idea behind the randomized controlled trial was to take away every single possible confounder except the thing that you randomized on. But here you've in essence, by putting in a pretest, introduced a confound into both groups, and worse, a confound that you can't particularly get a handle on. There are positives to pretesting, and so that so as I mentioned, you know, so the bias that we carry into this is that it gives you information on how comparable your groups are, and by putting in pretest scores into an ANCOVA model at the end, it actually increases the explanatory power of your statistical model, and so that so your model becomes smarter, and you explain more of the variance ultimately in the final outcome. And so the question then becomes, do these positives outweigh the negatives? And so that by pretesting, will I do better than if I hadn't had the pretest in the first place? And so that so Katie, can you put up the David Cook article for me? Perfect, thank you. So this is available for you to download, and this is a great article out of the Mayo Clinic by David Cook, who, if you've done any computer-aided instruction research at all, you know David quite well, because he's prolific in terms of his publications and records. And the table that I'm showing you is from his article, sort of up in here, where he talks at length about pre-testing and post-testing and the positives and the negatives. And so that I urge you to read that section where he goes through it in much detail and lays it out more lucidly than I can in the time that we have today. But let me go back to the PowerPoint. And I'll show you the points that he makes in terms of the way where the positives are and the negatives. Okay, so that in essence, a pretest helps you if you don't have very many people in your study. It's kind of the bottom line. So that if you're challenged for numbers, a pretest can help you by figuring out whether there is a difference in prior knowledge in your learners, and allowing you to factor that in, and to adjust your estimates of the post-test based on unevenness, sort of dissimilarity in terms of prior knowledge, and will help you in that sense. However, you suffer for that interaction, and so that the upshot of it is if you have sufficient sample size, then you're better off having a post-test only design. in that ultimately you won't have the interaction from the pretest, and yet you will at that point be able to tell on a between subjects manner whether or not there's a difference between the two. Now, other cases where you should consider using a pretest is if you already do a pretest, you know, so where you're studying a rotation and an obligatory part of that rotation is a pretest, and you use that those pretest results for other diagnostic purposes in presenting your education program, then away you go. And if you're using a non-randomized design, then that's a good place to use a pretest as well, because when you're not randomizing, then the risk of your groups having different there being a systematic bias wherein one group has more knowledge going into your study than another is quite sizable, and you want to have a handle on that, and you can accept the confounding that's going to happen. Okay. Anticipating a high dropout rate. If you're going to have a high dropout rate, then you have to explain that your dropouts are no different from your participants, and so that so having a pretest allows you to then be able to say, you know, sort of on pretest scores, there was no statistically significant difference between our dropouts and our participants, and therefore we can take these findings and generalize them to all learners, as opposed to just generalizing them to volunteers that persist with the study. So having a pretest is a good thing at that point. And then being able to generalize to a different population means that there's you have information that lets you know what level your group is at before any intervention is done, and therefore you can when somebody's choosing whether or not to do this intervention, that person can use your pretest results to discuss whether or to assess whether or not their learners are at the same level as yours are. So, bottom line is that there are pros and cons to using a pretest, and what is somewhat counterintuitive is that the pretests are probably more cons, if you can set it up properly, to using a pretest to not. There's a solution to this called the Solomon four-group design, in which you randomize people not to just your intervention and control, but you also randomize them to whether they get a pretest or not. And so that's what we're showing you here in this table, wherein there are four groups. And so that so group one gets a pretest, gets say the control, and then gets a post-test. Group two gets a pretest and gets the intervention and gets the post-test. Group three gets no pretest and the control and a post-test. And group four gets no pretest and the intervention and a post-test. And so that what this allows you to do is figure out whether or not the pretest is having any effect, and gives you a window onto the interaction of the pretest with your intervention. However, my take on this is that life's too short to do a Solomon four-group study. It means you have to double your sample size, and it means you have to worry about who's randomized to pretest and who's randomized to post-test, and complicates the whole thing a great deal. And so in terms of pretesting, the summary, what my take is that if you have the sample size, then do not use a pretest, and power your study to use just the post-test as your definer, whether you're going to get whether there will be a difference or not. If you don't have a large sample size, then use the pretest, but just be aware of the issues and report cautiously on the possibility that there's an interaction between the pretest and your intervention. And then if you're really using a Solomon four-group study solves this, but it's a complicated, difficult design, and so just be careful with that. Okay, next, let's talk about contamination. So, or rather, actually, we're going to look at comparable groups and clustering and talk about contamination there. So here's our typical study again. You meet your inclusion criteria, you get your pretest, say, or not. You get randomized, and then you go off into your intervention group and a comparison group, and then you go on to your post-test. Now, if you were studying a drug, that'd be great. This group gets the drug, this group gets a placebo, and so that when they arrive at the post-test, you know who got what. Okay, so that type of thing. The problem in educational studies is the fact that there's a certain amount of contamination that goes on. Okay? This group, the intervention group, gets the drug, but the drug leaks across Ward A and comes down and settles into the other students that are on Ward A. And so that if I developed a computer tutorial, or I did a sim, or I did whatever, A2 talks to A3 and says, wow, you know what I learned today? Blah, 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 blah. Which is great in terms of sort of delivering education across an uneven group of learners, but is bad for you as the investigator because you lose control over your drug and it spills across. And when contamination happens, it's the curse of the no significant difference study. And so that because what typically happens is that the education is meant to stay up here in the intervention group. It leaks across into the control group and then diminishes any differences that you were hoping to detect because of your new wonderful intervention. And so that there may not be any difference on the post-test if that happens. So these, what can we do about it? Well, there are a number of solutions, and so the solutions are kind of split up into either being at the study design level or at the analysis level. So the study design level, what you can do is you can overpower the study, so get so many participants that that whatever contamination happens, you still find the difference that's there. You can also do quasi-experimental designs wherein you randomize wards or randomize rotation months or randomize natural clusters in order to keep separate the students and minimize contamination. And then there are statistical ways that you can get around this as well. So here's an example of a quasi-experimental design. And again, you know, sort of it took me a long time to learn this, and that the first time I did a quasi-experimental study and wrote that down in a paper, my clinical preceptor said, don't ever put these words in there, you'll never get it accepted for publication. Because to a clinician, anything that's quasi-experimental means that it's not ready for prime time, and this is an inferior design. And yet, you know, sort of there are lots of these natural clusterings within our environments, rotation groups, wards, clinics, outpatient departments, attendings, you know, sort of a thing that we have to take this into account. A cluster randomized trial is taking this one step further in that we randomize clusters and not people. And so this is more and more being seen in knowledge translation studies where you randomize hospitals and the clinicians within a hospital and then take that into account. And then finally, there are great new statistical techniques called hierarchical linear models and generalized estimating equations that can take this into account as well. And in fact, a lot of the journals are now looking for the fact that you took into account the clustering that happened in your data. And the classic is, this stuff came out of educational studies, where they found that a difference between an intervention, sort of say this is intervention and this is control. Well, you know, sort of if I just compared little Johnny here to little Annie over here, I wouldn't get necessarily a good comparison because little Annie is in a class that's different from little Johnny's, and it may be down to the teacher that's the cause of the difference. And then this class might do better than this class because of the teacher, and not necessarily because I randomized this person to something different than this person. And then you can take it one step further, and that school A may do a better job than school B of providing its teachers with the ability to carry out your intervention. So you know, the whole idea is that stuff's nested, and that there can be variation due to these nesting levels, and that we can now take advantage, and we can now adjust for those on a statistical basis. So this clustering and the contamination that results because of it, we can factor out at the study design level, and we can factor out at the analysis level, but you need to think about it ahead of setting up your particular study. And when you're consuming education research, you need to look and see that people took into account these issues. And again, it's especially a problem in negative studies, and so pay attention there. Finally, in our is it valid sort of assessment, we need to think about the outcome measure. And this could be a 4-hour talk in terms of outcome measures, so whether or not they're reliable and valid. But I'm specifically going to take a look at reliability and give you kind of a brief overview of reliability and why it's important. Okay. So all good, sorry about the cursor. All good trials report the reliability of their outcome measures, and the phrase generally looks something like the reliability of our outcome instrument as measured by Cronbach's alpha was 0.74, and they come back with a number, and that number is meant to convey goodness with the higher the number, the better. But let's look at what that means. So the question is, sort of this is a sidebar, but validity is about whether you know that you're measuring what you thought you were measuring, and then reliability is about how well you actually measured it. And so I don't know if you've seen this target metaphor before, but it's a wonderful way of thinking about it. On the extreme left, we've got an assessment metric that is reliable, i.e., each time I take a measurement, it's very, very close to the other one, and so there seems to be a sense of the measurement and not a lot of dispersion around the measurement, so that the measurement I'm taking reliably gives me, as I repeat it over and over and over again, gives me roughly the same value under the same circumstances. But you can see that it's miscalibrated and way off. And so this is something that's reliable but not valid. Whereas if something, as I'm measuring it, each time I measure it, I seem to get a different number, and there's wide dispersion in the measurement, though it's centered on the mean is actually roughly right, then there's something that's not reliable but that is valid. And this is the situation that causes all sorts of problems in research. We don't even talk about something that's neither reliable nor valid, and so we're hopefully avoiding this situation entirely. And what we're hoping for is something where we've got a reliable measure, we measure it over and over and over again, and we get the same number, and that number has some basis in reality. So if we get a handle on reliability, our ability to sort of do this when we repeat it over and over again, getting the same answer, then we'll have a better outcome instrument, and we'll have more faith in our post tests and in what our studies showed. So here's an example that I was involved with. We took 750 medical students across 7 medical schools and had them do an 8-item pretest on carotid artery stenosis. And they did a computer module and got randomized to various arms, and then they took a different 12-item post-test on the same material. And what I'm going to do is sort of use these items to show you how reliability can affect the results. So here's the pretest. The pretest had, you can see here, 8 items on it. So each item is a row here, and we've got lots of observations. And within those items, they all kind of summarize over here to a Cronbach's alpha that is 0.47. Okay, so that I told you there are levels of goodness to this, and so we would love for this to be above 0.7 or 0.8, but you need a lot of questions to drive a Cronbach's alpha up that high. And so with 8 questions, this ain't so bad. Okay, so that where reliability hits practicality. And here's the post-test, and the post-test has more questions, so we were more concerned about the post-test, so we put 12 questions on it, and it has a reliability of 0.50. But it also has one item, sorry, let me get the pointer here, that's different than all the others, and so that so again, this is we can go into this in gory detail what the item rest correlation is, and it's also called a point biserial correlation. But the gist of it is that this one item, number 4, points in a different direction from the other 11 items. And what that means is that the people who did really well on the exam tended to get this item wrong, and the people who did poorly on the exam tended to get this item right. So it's the opposite of what you were hoping for, and so this item's behaving differently. And you can see over here in the alpha, if we subtracted that item, the alpha goes up from 0.50 where it is right now, and if we dropped the item, then the alpha goes up to 0.54. Remember, adding items is supposed to increase your reliability. This item is working so badly that it's hurting our reliability. And what does that mean? So we have pre-test data and post-test data, and so if we assume that the pre-test knowledge and post-test knowledge are correlated, then when we graph one against the other, here you have your score on your pre-test along the bottom and your score on your post-test along the top, we would anticipate that there'd be some sort of correlation between the two. And you can see here that there may be some correlation that you would imagine, but if I run a regression model, then the actual R-squared, this is a lousy model. It explains, the pre-test score explains 3% of the post-test score variance. And so that so it's a very, very weak association. But then, let's see what that one item does. If we drop that one item, what happens? Okay, so that here in this Stata run, we've dropped that item 4. That negative item is gone, and our Cronbach's alpha has gone up from 0.5 to 0.54. Okay, so a modest increase. But now when we correlate the pre-test to the post-test, everything else is the same. So along the bottom we have the pre-test score, and along the top we have the post-test score. And yet I think I can now convince you that there's an actual association between pre-test score and post-test score, with a high pre-test score correlating with a high post-test score. Life is working the way we anticipate that it should. And when I run the regression model now instead of the model explaining 3% of the variance, when I regress post-test score on pre-test score, now we've explained 18% of the variance, and that makes more sense. So our pre-test is typically correlated with the post-test at about sort of between 15 and 30% is what you're looking for. And so, so that clearly just dropping that one item, it did more in terms of improving our validity. Now these are dry numbers, and you should never, sort of just on the basis of psychometrics make these sorts of decisions. And so we went back and looked at the actual question, and the actual question looks okay. And what the issue was when you look inside the tutorial, there's the students who paid a lot of attention to the tutorial and extracted knowledge from it, there was and I don't remember the exact details, but the gist of it being that if you paid attention to the tutorial, then you answered this question wrong. And so that we had to go back and fix the tutorial in order to match up the content to what was going on in the post-test. So, but it's a nice example because it shows how the psychometrics can be used to sort of tell us that we're thinking about the world in the correct way. We're using an exam that has an internal consistency and internal structure, and that the numbers that we generate from that have meaning in terms of predicting what we want them to predict. So when you look at a Cronbach's alpha, there are levels of internal consistency that we shoot for, and so that so when you do your board exams, they shoot for a Cronbach's alpha of 0.95, 0.97, 0.98, and that's why you sit in that room for 6 hours and answer hundreds of questions. It's that they need to drive this up, and it takes a lot of questions in order to get it up there. Whereas if you're, sorry, don't know quite how I did that, but I did. So that, whereas if you're asking only a few questions all told, then you've got to settle for lower Cronbach's alpha, but you need to understand that that's the compromise you're making. And the thing is that the more noise there is in your estimate of that your outcome instrument is providing, the less power you're going to have to detect a difference. And so you have to compensate for that. And I won't belabor these formulas, but the gist of it is that if you see here, this R is the value of Cronbach's alpha. And so that the higher the Cronbach's alpha, the smaller the standard error of measurement. And the smaller the standard error of measurement, the tighter your 95% confidence interval is. Okay? So that so just remember that your Cronbach's alpha is tied in tightly to the confidence interval that you're going to have around your outcome score. So in summary here, the convex alpha gives you a sense of sort of how good your outcome instrument is in terms of reproducibility. And so that your outcome instrument, it has to go through some validity checks, but if it's not reliable, even if it is valid, you're going to have a hard time proving what you want to prove. So that so my advice is to pilot test your outcome instrument and pay attention to that and make careful judgments about how many questions you're going to use. And so that so it's difficult to get people to sit still for exams, and yet in order for you to make sense of your results, you're going to need a tight confidence interval to do that. Generally, medical schools worry about this in terms of sort of their outcome assessment instruments, and so there's generally somebody at every medical school who worries about this stuff, and they can help you with your research. Good. Okay, so that I've gone through these three items: contamination, pre-testing, and measures of reliability, and so that so at this point I'd be happy to throw it open to questions.